Okay, so today's lecture I will start again with simultaneous equation only. We have derived two formulas, one for Cx and one for Cy. Now, in actual practical, when you are actually conducting this experiment of simultaneous equation method, you can take any compound as X and the remaining compound as Y. There is no condition के जिसका नाम पहले आया उसको CX बोलना है and the other compound should be compound Y. No, it is not like that. Okay. Now, there is some trick to remember these formulae. If you see the denominator for both the formulae, they are exactly same. Okay. So denominator, it is easy to remember. It is always ax2 ay1 minus ax1 ay2. Okay. In the numerator also, these terms are same. That is capital A followed by small a. Capital A followed by small a. So this is again common in both the equations. I hope this is clear. Now, when you are talking about X, that is Cx, in the numerator you have Ay. At both points you have Ay. When you are talking about Cy, in the numerator you have Ax. अभी यहाँ तक आई होप कि आपको याद रहेगा. डिनोमिनेटर दोनों का सेम है. न्यूमरेटर में कैपिटल ए फॉलोड बाय स्मॉल ए, कैपिटल ए फॉलोड बाय स्मॉल ए, कैपिटल ए फॉलोड बाय स्मॉल ए, ऐसे लिख देना है. इफ इट इज Cx, आफ्टर स्मॉल ए राइट डाउन y बोथ टाइम. मतलब यहाँ पे भी आप ay लिखेंगे और यहाँ पे भी ay लिखेंगे. अगर आप Cy के लिए सोच रहे हो फॉर्मूला लिखना, देन यू विल राइट ax ओवर हियर एंड ax ओवर हियर आल्सो. अभी when you are talking about Cx, it is 21 12. अब ये 21 12 क्या है? That is कैपिटल A के बाद आपको 2 लिखना है, स्मॉल ay के बाद आपको 1 लिखना है. Then again after capital A you will write down 1 and small ay you will write down 2. This is for Cx 21 12. Okay, remember Cx is equal to 21 12 and Cy is equal to 12 21. So if you remember like this, remembering formula will be easy for you. Okay, क्या क्या याद रखना है? डिनोमिनेटर दोनों का सेम है Cx और Cy के लिए. न्यूमरेटर में दोनों जगह पे क्या लिखना है? कैपिटल A सो फॉलोड बाय स्मॉल a. अगर वो Cx है तो स्मॉल a के बाद ay लिखना है, और अगर आप फॉर्मूला लिख रहे हो Cx के लिए तो स्मॉल a के बाद x लिखना है, और उसके बाद ये 21 12 12 21, इतना याद रखो. ओके, आई होप it will be easy for you now to remember this formula. Now, we will start with another method. This method is called as absorbance ratio method. So write down today's name, today's date, I'm sorry, and then write down name of this method, absorbance ratio method. When you have any doubt, if you have doubt, you will unmute yourself and ask me your doubt. Because when I'm focusing on presentation, I'm not looking at window, my browser window. Okay, so this absorbance ratio method is modification of simultaneous equation method. Okay, it is just a modification. So when I'm saying it is modification of previous method, all the conditions, the assumptions, and criteria will remain same. ऑब्वियसली अगर मॉडिफिकेशन है तो कुछ तो चेंज होगा. So we are changing very slight thing. We will see what we are going to change. But criteria and assumptions will remain same as simultaneous equation method. Now, it depends on the property that for a substance which obeys Beer's law, at all wavelengths, the ratio of absorbances at any two wavelengths is a constant value, independent of concentration of the path length. Now, this statement you may think is a little bit complicated. I will simplify that. Okay, consider this particular curve. Okay, suppose ये solution है किसी drug का. Suppose it is solution of say aspirin. It is solution of aspirin at particular concentration. When I scanned aspirin over certain wavelength range, I got 2 lambda max. This is 1 lambda max and this is second lambda max. At first lambda max, the absorbance at say first lambda max is approximately equal to 1. Okay, it is approximately equal to 1. If I take the second absorbance A2, it is approximately 0.5. It is approximately equal to 0.5. So, what is the ratio A1 upon A2? It is equal to 1 divided by 0.5. So this ratio is nothing but, or this is equal to 2. Now, the same aspirin solution, I added unknown quantity of say ethanol, methanol, water into it and I diluted that solution. For that diluted solution, I will get lambda max at same two wavelengths, that is wavelength 1 over here and wavelength 2 over here. At these two wavelengths, I will get lambda max. I measured the absorbance at first lambda max. Let us call it as A1 dash. It was approximately equal to 0.6. And when I measured absorbance of that same diluted solution at second lambda max, it was approximately equal to 0.3. It was approximately equal to 0.3. So in this case, if I calculate ratio of absorbances A1 dash upon A2 dash equal to 0.6 divided by 0.3. So is it not the same as the previous, although the concentration was totally different? So this is the property which is constant if a substance is following the Beer's law. Now I will read again. This time I'm sure you will understand it better. This particular method depends on the property that for a substance which obeys Beer's law at all wavelengths, the ratio of absorbances, the ratio of absorbances, at any two wavelengths is constant value. See, the value constant over here is 2. Is constant value independent of concentration or path length. In this condition, we change the concentration. Similarly, if you change the path length, the range will, the value of the ratio will remain same. Okay, so this is the property we are going to use in this method. If you have doubt in this property, please ask me, otherwise I will proceed further. Okay, for example, two different dilutions of the same solution give same absorbance ratio A1 upon A2 is equal to 2.0 as in the figure. Now, in USP, this particular ratio is referred as Q value. In British Pharmacopoeia also, it also uses a ratio of absorbance at specified wavelengths in certain confirmatory test or identity. They have not given any name to this ratio, but they also use it. The method is referred as Q ratio method in USP because they are naming this ratio as Q. Okay, so other name for absorbance ratio method is Q value method or Q ratio method. Okay, I want you people to copy down this slide, take down, uh, quickly copy down even this image also. Mukesh, you will unmute yourself and tell me when it is done. Observe this particular diagram over here. This diagram is very similar to diagram we use for simultaneous equation method. There is one curve missing, that was for the combined absorbance of X and Y. So instead of that, we have only X ka curve and Y ka spectra. Okay, X ka spectra and Y ka spectra. Now, if you observe carefully, you have marked here only lambda max of Y, and you have marked a wavelength on the graph at which absorbance of X and absorbance of Y are same. Okay, that wavelength at which the absorptivity of X and Y it is same, that point, that wavelength is called as isoabsorptive point. Okay, this is favorite question for examiners in Viva. This is favorite question for that first question, 1 mark question. यहाँ पे definition पूछते हैं. Okay, so in the quantitative assay of two components in admixture by the absorbance ratio method, that is this method, absorbances are measured at two wavelengths. One wavelength, which is lambda max of one of the component, you can see it over here, and the other being wavelength of equal absorptivity of two components, is lambda 1. Here we are calling this wavelength as lambda 1. It is an isoabsorptive point. Now, no matter if you take different ratio of concentration or substance X, okay, at all concentrations, the ratio of absorbances at lambda 1 and lambda 2 is constant. I repeat this statement. For X, for substance X, the ratio of absorbance at lambda 1 and lambda 2 will be constant. Similarly, for substance Y, the ratio of absorbance at lambda 2 and lambda 1, this ratio will also be constant. Now, one more thing. Here we are talking about absorbance. Here we are talking about absorbance. We can also talk about absorptivity in similar manner. What is absorptivity? Absorptivity is absorbance divided by concentration when path length is unity. that is path length is equal to 1. So although this particular graph is for absorptivity versus wavelength, it is absorbance versus wavelength, that is absorbance on y-axis and wavelength on x-axis. The graph of absorptivity will be pretty much similar, and there will be a point at which both the absorptivities are matching. Remember what I'm saying. I'm saying absorptivities of x and y are matching. That is, absorptivity of x at lambda 1 is equal to absorptivity of y at lambda 1. Okay, please copy down this slide. If there is doubt related to concept, unmute and ask. Please copy down this slide with diagrams. Yes.
सर वो y कंपोनेंट का जो एब्जॉर्बेंस है वो लैम्बडा 1 को कम है और लैम्बडा 2 को ज्यादा है, और इन केस ऑफ सब्सटेंस x उसमें मतलब लैम्बडा 1 में उसका एब्जॉर्बेंस ज्यादा है और लैम्बडा 2 में ज्यादा, तो इसका रेशियो सर अलग अलग आएगा ना?
रेशियो अलग अलग ही आएगा, लेकिन सिर्फ हम x के लिए देखें. ओके, तो x के लिए वो कांस्टेंट है और y के लिए वो कांस्टेंट है, और दोनों का वैल्यू फर्स्ट वेवलेंथ पे सेम रहेगा. मैंने जो बोला आपको समझा? देखो कम ज्यादा होने दो ना, लेकिन अपने को इंटरेस्टेड क्या है, वो कांस्टेंट होना चाहिए. वो कुछ भी रहे, ज्यादा रहे कम रहे, कांस्टेंट होना चाहिए बस. और हम एक वेवलेंथ यहाँ पे ऐसे सिलेक्ट कर रहे हैं कि एब्जॉर्प्टिविटी एक्स और वाई का दोनों का सेम है. आपका डाउट क्लियर हुआ अक्षय?
यस सर, यस सर.
Okay, have you understood the previous slide? Okay, whatever that graph in the first slide, first diagram, suppose वो X compound है, ठीक है? Hello, you need to unmute yourself. I need feedback from you.
Yes sir, yes sir.
Please unmute. Okay, suppose that is component X. और ऐसा ही कोई तो दूसरा एक ग्राफ है, दूसरा एक स्पेक्ट्रा है, वो कंपोनेंट Y है. तो A2 upon A1 for X is constant.
Yes sir.
And A2 upon A1 for Y, it is also constant. Now we are taking one special case when we have both X and Y together in the solution.
Okay.
So we need to select two wavelengths. One wavelength is lambda max of Y. The other wavelength is a common wavelength at which the absorptivity of X and Y are same.
Yes sir.
Okay.
Yes sir.
अभी यहाँ तक समझा क्या?
Yes sir.
Okay. It is good that you asked your doubt. You can mute yourself now.
Sir.
Till the point, yeah.
Sir, this is
Please ask.
for the determination of Y. Can this also be used for the determination of X?
Who told you that it is only for determination of Y? With this formula, whatever we are going to derive, we can determine both X and Y, irrespective whether we are selecting lambda max of Y or selecting lambda max of X. We are taking reading for both X and Y.
Okay, sir.
It is just which wavelength to select. To select one wavelength which is common to both the substances. When I'm saying common, it means it is giving same absorptivity or same absorbance. That wavelength we are going to select, and the second wavelength it should be lambda max of X or lambda max of Y. दोनों में से किसी का भी चलेगा.
Okay, sir.
ठीक है? हाँ. अभी तक जो हम कंसिडर कर रहे थे, when we are thinking about the ratio of A2 upon A1, we were thinking of ratio of only X and Y. But the same method can be extrapolated to mixture also. Okay. So when we are taking absorbance of mixture at one wavelength, and absorbance of the same mixture at the other wavelength. The ratio of absorbances will depend on the ratio of x and y. I will not confuse you more by telling you without showing anything on the screen. If you permit, I will change the slide now. If you are done writing, any one of you can unmute and tell me whether should I proceed or not.
Done, sir.
Okay. Okay. So in previous derivation, we had derived equation 1 and equation 2. Okay. The two equations are constructed as described before for the method of simultaneous equation, that is equation 1 and equation 2. Their treatment is somewhat different. However, we are going to use the relationship AX1 is equal to AY1. What is AX1 is equal to AY1? We are talking about this point. Absorptivity of X at first wavelength is equal to absorptivity of Y at first wavelength. That's why AX1 is equal to AY1 at lambda 1. We are going to assume that B is equal to 1 centimeter. So, as it was in the previous derivation, at lambda 1, observed absorbance of solution, that is capital A1, is equal to absorptivity of X at this first wavelength multiplied by concentration of X in the solution, in unknown solution, plus absorptivity of Y at first wavelength multiplied by concentration of Y in the sample solution, unknown solution. Similarly, at lambda 2, observed absorbance, that is observed absorbance of the solution at second wavelength, is equal to absorptivity of X at second wavelength multiplied by concentration of X in the solution plus absorptivity of Y at second wavelength multiplied by concentration of Y in that same unknown solution. I think these two equations are very clear to you. Quickly write down these 4 or 5 lines. I will give you 1 minute. There is no diagram, so write down quickly. इसमें कुछ doubt है तो पूछो. I hope you are done writing now. Okay. In the next step, we are going to divide the numerator and denominator of right hand side by Cx plus Cy. Okay. Now, we want to simplify this ratio, and we want to use this ratio for determining Cx and Cy. Okay. So for that, we have to carry out certain algebraic operations. Okay. So first operation in that sequence is dividing numerator and denominator by Cx plus Cy. Now consider only this term, ax2 Cx. X2Cx divided by Cx plus Cy. Now this can be written in this manner, Ax2 multiplied by Cx upon Cx plus Cy. Similarly, this second term can be written as Ay2 Cy upon Cx plus Cy. Similarly, I am writing down the denominators. So it is Ax1 Cx upon Cx plus Cy and Ay1 Cy divided by Cx plus Cy. Now, you will understand that there are these two terms common. Which are those? Cx upon Cx plus Cy and Cy upon Cx plus Cy. Let us consider this entire term as fx, that is function of x. यहाँ पे numerator में Cx है, उसको consider करेंगे fx. And the other term where we have Cy, that is y in the numerator, we will consider it as fy, that is function of y. So what we get as this ratio is, please observe over here. So A2 upon A1 becomes AX2 fx plus AY2 fy divided by AX1 fx plus AY1 fy. Okay, I hope you have understood this. Please copy down the remaining slide. This is the equation you have got. Now, please note that fx plus fy is equal to 1. Now, let me prove it. What is fx? It is cx upon cx plus cy. And what is f of y? It is cy upon cx plus cy. So if I add this, what I will get is nothing but cx plus cy divided by cx plus cy. So this is equal to 1. That's why it is written as fx plus fy is equal to 1. That is, fy will be equal to 1 minus f of x. Okay, so all fy we will substitute with 1 minus fx. So you will get this equation. Okay, after getting this equation, we will open this bracket. So ay2 multiplied by 1, it is ay2 again, minus ay2 multiplied by fx, you get ay2 fx. So this is the numerator you have got. Now in the denominator, this term remains same as it is. The second term, ay1 multiplied by 1, so ay1 again, minus ay1 into fx, it is ay1 fx. So this term you have got. Now please open the brackets and terms containing fx, bring them together. Okay, so see, I have taken these two terms containing fx near and ay2 at the end. Similarly over here, this term and this term containing fx taken together, ay1 at the end. Once you have that, you can take f of x common. So f of x you can take common from these two terms only, not from third term, because there is no f of x. So fx in bracket you get ax2 minus ay1 plus ay2, and in the denominator fx in bracket ax1 minus ay1 plus ay1. But ax1 and ay1 they are same. That is, absorptivity of x at first wavelength is equal to absorptivity of y at that same wavelength. Okay, so subtracting one term into the same term, this term will become 0. So multiplication of fx to that 0 will also become 0. So in the denominator you get only ay1. So please complete till over here. Copy down the entire slide and let me know. If you have doubt, please ask me. So in the next step, see, I have written down the same equation again, which was there on the last slide. Okay, observe this equation. We are going to expand this equation. How? The denominator, we are going to divide it with every term in the numerator. We will open this bracket and then we will divide these three terms with ay1. So first term will be fx multiplied by ax2 divided by ay1. See, fx multiplied by ax2 over here divided by ay1, minus fx remains same over here. देखो ये fx multiplied by ay2. So fx multiplied by ay2 divided by ay1 plus ay2 divided by ay1. This is the last term. Okay, now you will observe that in the two terms it is ay2 upon ay1, ay2 upon ay1, but here it is ax2 upon ay1. Can we replace this ay1 with ax1? Yes, because ax1 and ay1 both are same. So we are going to replace ay1 with ax1. So after replacing, the term becomes fx ax2 upon ax1 minus fx ay2 divided by ay1 plus ay2 upon ay1. Okay, after you have reached over here, we have got three terms which are very similar. देखो ये दोनों terms same है, ay2 upon ay1, ay2 upon ay1, and this is ax2 upon ax1. ये जो रेशियो है ax2 upon ax1, let us call it as qx, and ay2 upon ay1, let us call it as qy, and the ratio of a2 upon a1, we will call it as qm. M here stands for mixture. Okay, M stands for mixture. So after we have these Q ratios placed, we have these Q assumptions, you get the equation as Qm is equal to Fx multiplied by Qx minus Fx Qy plus Qy. Now, if I rearrange this term in terms such that I have Fx on left hand side, I get Qm minus Qy divided by Qx minus Qy. देखो ये यहाँ पे Fx common है, you can take that Fx common, so in bracket you will have Qx minus Qy. Okay, you can bring this term Qy on left hand side, so it will become Qm minus Qy. So Fx will be equal to Qm minus Qy divided by Qx minus Qy. यहाँ तक लिख लो. I will give you 2 minutes to write. Hurry up. इसमें कुछ doubt होगा तो पूछो. Very good. If you look at this final expression, final equation, you will find that we want to find out Cx and Cy. There are no such terms as Cx and Cy. There is neither Cx, neither Cy. How can we find them? So we need now to replace f of x with its original meaning. See, f of x is equal to Cx upon Cx plus Cy. So now Cx upon Cx plus Cy is equal to Qm minus Qy divided by Qx minus Qy. Okay. If we rearrange, I want only Cx on the left hand side, so I will have to take Cx plus Cy on the right hand side. Okay. Cx plus Cy on right hand side of this expression. To get Cx. Now, see, A1 is equal to Ax1 Cx plus Ay1 Cy. That is, A1 is equal to Ax1 Cx plus Ax1 Cy. देखो हमने क्या किया है, Ay1 को रिप्लेस किया है Ax1 से. Okay, so can I take Ax1 common? Yes, I will take Ax1 common, so I will get the equation as A1, that is absorbance at first prevalence, is equal to Ax1 multiplied by Cx plus Cy. So what is Cx plus Cy is equal to? It will be A1 divided by Ax1. So Cx plus Cy is equal to A1 upon Ax1. So can I replace this over here? Yes, I can replace. So Cx is equal to Qm minus Qy divided by Qx minus Qy multiplied by A1 divided by Ax1. Okay, this is the final expression. Now, using this expression, we can find out Cx. Similarly, we can derive equation for Cy. For Cy, there will be very slight difference. Qm remains as it is. Minus, यहाँ पे Qy है, तो यहाँ पे क्या आएगा? QX, यहाँ पे QX है, यहाँ पे क्या आएगा QI, यहाँ पे QI है, यहाँ पे आएगा QX. A1 remains same, and instead of AX1 we are writing AY1. Basically they are same expression, we have discussed this. AX1 is equal to AY1, but when you write CY, you have to write AY1. So here our derivation is complete. Now, what is QM? QM is A2 upon A1. What is QX? It is AX2 upon AX1. And what is QY? It is AY2 upon AY1. Now, using this equation and using this Q ratio, how can we find out? Concentration of EX and CY in the unknown solution? So, you must have three solutions ready with you. Which are those three solutions? First solution, obviously your unknown solution. From that unknown solution, can you find out A2 upon A1? It is simple. Take that solution, take absorbance at first wavelength, take absorbance at second wavelength. Take the ratio of two absorbances. You will get your value of QM. You can substitute your value of QM over here and over here. Now, you prepare one solution which contains only X. This is your standard solution. Okay, I repeat, you will prepare second solution only consisting of X. At wavelength 1 and wavelength 2, take their absorbances. Absorbances you divide by concentration. ये आपका standard solution है X का, तो आपको concentration पता है. तो absorbance divided by concentration, you will get absorptivity of X. So you determine AX1 and AX2. When you have AX2 and AX1 value, you can determine QX. If you have QX, you can substitute that QX over here. You can substitute QX at these two positions. Similarly, when you find out AY2 upon AY1, it will be easy. Prepare a solution which contains only AY. Take its absorbance at both the wavelengths. So you have values of absorbance at both the wavelengths. Divide that with concentration of Y in that standard solution. So you will get AY2 and AY1. You take this ratio, you will get QY. So you can substitute that QY over here and over here. You already have values of A1. A1 क्या है? Absorbance of the solution of the mixture at first wavelength. So you have these values. You also have values of X1 and AY1. If you have all these values, you can definitely determine CX and CY from unknown solution. If you have no doubt, please copy this down. If you have any doubt, unmute yourself and ask your doubt. Please copy down the slide. This is the end of derivation of this method. Criteria and assumptions for this method are same, exactly same as the simultaneous equation method. Additional criteria over here is what we may express in terms of algebraic. X1 is equal to AY. Isoabsorptive force. This is wrong for me to refer brackets as well. I need to refer brackets for that. But you can search on internet what is the law of isoabsorptive. If you have understood the concept, it will be easy for you to find. Okay, anyway, the lecture is ending. If my voice is breaking, it is because of the rain has started. It's been raining heavily. So maybe because of that, my voice is breaking. So what I request you is write down your roll number in the chat box